from NIT Varangal in 2018. Currently, Sar has working as professor in the Department of Electrical and Electronics Engineering in SR University, Varangal, Telangana. Sar has published various international journals and conferences on application of artificial intelligence in electrical engineering, integration of renewable energy into the power grid, power system deregulation, power system state estimation, and object detection using deep learning techniques and sequential data processing using recurrent neural networks. Sar is also acting as a director of the Center for Artificial Intelligence and Deep Learning. Sar has an official instructor for NVIDIA Deep Learning Institute. Thank you, sir. Thank you, everyone. Once again, I heartily welcome to this session, sir.
Yeah, thank you,
Sandeep sir. So now I request Dr. Venkataramana Veramashetti sir, please continue this session, sir.
Sure, sir. So thank you very much, Sandeep sir, for a nice introduction, and also thanks to Anil sir for giving this opportunity.
Thank you, sir.
So, yeah, I hope my voice is clear to all the participants.
Clear, sir. Audible.
Yes, thank you. Is it screen is visible to all?
Yes, sir.
Yeah, fine, sir. And good evening to all the participants. Today I'm trying to give some discussion on AI and ML applications in the distributed energy resources. So there are the multiple applications where we can correlate both AI and ML with the distributed energy sources. So distributed energy sources may be a conventional energy sources or the non-conventional energy sources also, like but small scale capacity. Like distributed generation may be a generators from the diesel engines, or that may be from PV panels, that may be from wind energy. So all comes under the distributed energy sources, so which are integrated in the distribution system. So this is the actually broad topic. So AI and ML in distributed energy resources. And in that broad area, I'm trying to narrow it, and I'm trying to focus on a small problem, which can be where we required AI and ML in the distributed energy resources applications. That small topic or a narrow topic is this one. That is the economic distributed generation for optimal operation of active distribution system using game theory. So this is the problem I'm trying to discuss in today's session for the next 1.5 hours approximately. So let's justify the title, Economic Distributed Generation for optimal operation of active distribution system. So what mean by active distribution system? So we all know distribution system, where in the distribution system where power is supplied from the substation to the load centers. That load centers may be a domestic or commercial or industrial, but the flow will be from the substation to the load centers, right? So that is just a distribution system, or we can call it as a passive distribution system. Whereas nowadays we are integrating DGs, that is called distributed generations, or sometimes it's also called as the embedded generation. We are integrating the different DG units or EG units. Those units may be a PV systems, or maybe a windmills, or maybe a small scale generation. So we are integrating in the distribution system. So now power, we can't say that power will be flow from the substation to the load centers only. There may be some power will be injected at the load centers also. Let's assume at home you have some sufficient capacity, sufficient size PV panels are there. Then you can inject the power into the grid. Then power will be injected into the network, distribution network at your home also, at your load point also. So power in passive distribution system, power will be injected at the substation point or the substation bus. But where in case of the active distribution system, power will be injected in multiple load centers also, at multiple load points also, power will be injected. So that is called the active distribution system. Simply call it as the active distribution system is nothing but the distribution system with multiple distributed generation units. That's it. The distribution system with the multiple distributed generation units. That is called the active distribution system. Now coming up, optimal operation of active distribution system. What mean by optimal operation? So actually optimal operation may be we can consider the different parameters. Optimal operation in terms of the active power losses, optimal operation in terms of the emissions, optimal operation in terms of the reliability. So any parameter you can consider. So we are trying to operate the network optimally based on that parameter. Or maybe you can consider the combination also. So what I mean to tell you is optimal operation of a network measured in the different aspects. One is maybe in terms of the losses, in terms of the emissions, in terms of the reliability, in terms of voltage stability. So different parameters we can observe the operation. So we are trying to maximize the operation. We are trying to optimize the operation of a distribution system in terms of all these parameters. And those parameters need not to be a single one. You can combine. You can combine losses and emission. You can combine losses, emission, reliability. You can combine losses and voltage stability. So you have to operate in the specific parameter in a better way. That's called optimal operation. Optimal operation means you are trying to maximize the operation in terms of the losses, in terms of the emissions, whatever it may be. You are trying to operate your network more efficiently. That's called an optimal operation. I hope you understand. So optimal operation. In this topic, I consider the losses. So optimal operation in terms of the losses means I'm trying to minimize the losses. I'm trying to minimize the losses. Hope you clear. So optimal operation means it may be you have to operate the network at a minimum losses. You have to operate the distribution network at the minimum emission, or you have to operate the network at the maximum reliability, right? So, or you can operate the network at the maximum voltage stability. So these are the different parameters where we can consider for the operation of the distribution system. So, but whereas in this topic, I am considering the losses. That means optimal operation of active distribution system is nothing but operating the active distribution system at the minimum losses. That's my goal. So if I want to operate the system at the minimum losses, go up slightly. That what is that one? Economic distributed generation. That means how you can economically play with the distributed generation units. How you can play with the distributed generation owners financially, economically, so that your active distribution system will be operated optimally in terms of the losses, so that your active distribution system will be operated with the minimum losses. That's what. How you will play with the DG units, how you will play with your DG owners in terms of the financial incentives, in terms of the economic aspects, so that your active distribution system will be operated optimally in terms of the losses. I think I justified my title. Hope everyone is following, everyone is able to understand the title. Now we move inside. So what is the approach? How we can operate economical operation of distributed generation? That we will discuss. So this is my content. So first is the problem description. That's how I completed now. Next, load forecasting is required. So the load forecasting using ANN, and load flow is also required. That's the backward and forward sweep load flow algorithm. And a linear programming problem also required. Nucleus theory, that's called one of the game theory concept. And iterative algorithm and some results we are trying to discuss. So mostly, as my given time is up to 9 o'clock, we'll try to finish as per the schedule. Okay. Now, come now. So coming to the problem description, just now I explained. Now going to the some introduction. So previously, that means in the 90s, our power system network is a vertically integrated electric power system network. So vertically integrated network means all the generation activities, transmission activities, and distribution activities are under the single authorization body. That is under the control of government or single body. Both generation activities, distribution activities, transmission activities. So that single body, single organization is responsible for the generation, for the transmission, for the distribution of the power to the various customers. To the various customers. Right? So later on, what happened is the restructured power system is coming to picture. So restructured power system means that the generation activities are separated from the transmission and distribution, and the competition is encouraged in the generation by encouraging the participation from the private owners. Private owners. That means we have the multiple power plants which can be authorized, which will be operated by the private people, not by the government. So they can participate in the generation. So from that aspect only, the private people are entering into the electricity market in the form of the power plants. So generation activities are separated from the transmission and distribution, and encourage the competition in the generation activities by inviting the private people. So that expecting once the competition is there, then the expecting that we can get the better quality, right? Suppose in a area I am maintaining or only there is only one school. At in a particular area, there is only one school. There is no competition. Then the management feel that whatever we deliver, we can deliver, no problem. Admission will come automatically. But if there is one more competition, then the people are thinking that we have to do something better than the other. The competition, then the better output will be coming. That's the reason why the private partners are entered into the generation, and the competition is encouraged in the generation activities to get the better output. Right? Now, transmission and distribution are mostly under the single body, like a government, and whereas in some metro cities, some private sectors also take over transmission nowadays. So there is some market structures and everything will be there. Market structures means, the industries, customers, let us say industrial customers, who are the large customers, they will enter into the market. They will place a bid for at this point of time, this amount of power is required. And similarly, generation companies also place a bid in the market. At this point of time, this amount of power we are able to sell. Then there is a deal between the customers and the generation companies in the market. So that's called as your energy market. Okay, this is the energy market. In the energy market, the deals will be closed. And based on the closed deals, in the real time, that operation should be happened. And in between, there is one more parameter that is called ISO, Independent System Operator. So what he will do? He will not take care of any financial aspects, the bids and everything. He will not take care of. What he will take care is, once a deal is closed between the two parties, either generation company with the customers, then he will check whether that deal is feasible technically for a given transmission network or a given distribution network by running the load flows, all the things. He will tell whether the network is feasible for that deal. There is any congestions. So is there any overloading? So all the technical parameters he will take care of it. So this is the structure of your electric power industry. Now, as I said earlier, in a distribution system, previously the passive distribution system, power will flow from the substation to the load centers. But because of the integration of the DGs, penetration of the DG units into the distribution system, it becomes active. But why we need to integrate the distributed generation? We need to penetrate the power from the DGs into the distribution network. What is the use? What are the benefits? So benefits are, one is the reliability improvement. That means suppose if Actually, it's the radial structure. Most of the distribution systems, of course, distribution systems, distribution networks are the radial structures. If any line coming from the substation, main substation is breakdown, then the area under that bus, that line will don't have any power in case of the passive distribution system. But in case of the active distribution system, if any line is broken between the substation to the particular area, at least in that particular area, some power can be restored based on the distributed generation units. That's what reliability will be improved. And coming next one is the emission reduction. If there is no distributed generation units, we are taking the power from the main grid, and main grid got the power from mostly from the thermal power stations, where there is a more number of emissions. But if you are integrating your distribution network with a small scale DG units with less emission generators like solar and wind, small scale, then definitely your emissions will be reduced. Right? Let's assume in a particular area we require 100 megawatt of power. If there is no DG units, all 100 megawatt of power can be taken from the thermal power station. Let's assume you have some DG units which are able to supply 20 megawatt, then you can take 80 megawatt only from the substation. When the power delivered from the main plant is reduced to 100 to 80, definitely the emissions also reduced. So that's why that's the emission reduction. Similarly, improvement of the electric distribution network reinforcement origin. So what's the reinforcement origin? So reinforcement origin means if we place one fader from one area, one substation to the one particular area, there is some reinforcement origin. That means at the time of the placement, they will calculate based on the growth rate how many years this fader can sustain based on the growth rate. For example, if they place the current load for a particular area is equal to 20 megawatt, like I assume, they will not place a fader which is capable to holding the 20 megawatt of power. They will place up to 50 megawatt, and based on the growth rate, they will estimate. So maybe after 10 years, up to 10 years, so this fader can withstand. So but after 10 years only, the powerful limit may be crossed 50 megawatt. So that 10 years is called the reinforcement origin. But that reinforcement origin, the 10 years increase it to 15 years if you are able to integrate the DG. You are able to integrate the DG. Similarly, utilization of non-conventional energy sources, there may be loss reduction, and also you can avoid the investment in the large power plants and the transmission lines, right? If you are able to supply small generation at the distribution level, you can avoid. I am not saying that there is no need of establishment of the large power plants. There is required based on the improvement of the growth rate, but it can be avoided up to some extent. Up to some extent, you can avoid the establishment of the new plants or replacing the new transmission lines. Right? So these are some benefits of the DG. So which will help, which will motivate to integrate the DG units into the distribution system. Now coming to the highlights of the Electricity Amendment Bill of India in 2014. I want to tell one thing. I was joined in NIT Warangal as a PhD scholar, as a research scholar in 2014 December 18. 2014 December 18, right? By that time, generally I came, just I defended my MTech thesis, the optimal placement of the distributed generation units, and there is no idea whether I can proceed with the optimal placements or some other topic. I don't know at that moment. But one day I went to a library and opened my notes. So that means opened that some newspaper. In that newspaper, I saw this one, 2014 Amendment Bill, that motivates me to work in this direction, power system deregulation, especially in the distribution side. So that motivates me. So coming to this point, what are the main points in the 2014 Amendment Bill, the Electricity Amendment Bill? Till now, transmission and distribution are there, right? In the distribution, network, as per the 2014 Amendment Bill, the distribution network operations should be separated from the business operations. As of now, all are under one control. You can agree. So your operation of the network and also supply also under the only one distribution companies only as of now, but not implemented. That's a bill. Okay. So now what that bill is saying that separate that business activities, like financial related, from the distribution network operations. Distribution network operations. Distribution network operations are technical. Financial operations are the economical or whatever business point of view. These two activities should be separated. That's the main theme of that one. Now, once the separated business activity or supply related stuff and the network operations is separated, now introduce the multiple supply licenses. So let us assume, I want to give some clear idea. Let us assume in Warangal distribution network, the complete network operations, like the network operations placing the faders and calculating the its limits and observing the flows. All the network operations will be done by the distribution companies, and whereas who will supply the power? So that can be taken care by, that can be given to the private agencies. So the multiple private agencies will come and they will sell the power with this distribution network. So the distribution company will not take care of that financial benefits, financial stuff. So at what rate you can sell the power, all the things will be taken care by the private supply licenses. Hope you understand. Hope you understand, right? Technical will be taken care by the distribution company, whereas economical perspective, that means purchasing the power from the grid and selling it to the local customers, that will be taken care by the private people. There we can encourage the multiple licenses. Anyone can place a bid. So based on their bid, they will give the license for those people for that particular area. So when the private players are entered here, then definitely expecting that some competition again, that may give some better quality of the power. Service also, better service. That's the main theme of that one. The State Electricity Board Commissions, SERC, will provide the license to supply. Who will give this license for the private people to supply the power to a particular area? That is the SERC, State Electricity Regulatory Commissions. In a given area, the supply, consumers can opt. In a given area, like in Warangal area, the consumers will opt any. They can opt a person A, they can opt a person B, or they can opt a person B, C, whatever it may be. Any license he can opt to get the power. Like in our mobile network, I can use a BSN, you can use a Geo, some people can do Airtel in a Warangal area. So anyone can use. They have the towers. So like that, this is what. In case, if any supply license seized, if the supply, like there may be even though encouraged for the private people, that can be more observed, and they have to obey the rules and regulation of a government agencies. If anyone violates those one, their license will be seized. Once the license is seized, then who will supply the power to the customers under that supply licensee? That part will be taken care back by your provider of last resort, that's called POLR. So that's nothing but the SERC. Your POLR is nothing but the state electricity boards that will take care. So these are the key informations in that bill. So I think this structure will not be available anywhere, that we draw this thing. So restructured electricity system based on the electricity amendment bill of India 2014. Based on the amendment bill, just we prepare this diagram. So now previously generation is separated, now distribution is separated. Again in the distribution network, that there is a distribution licensee who will take care of the network operations, and there is a supply licensee who will take care of purchasing the power from the market and selling the power to the customers. He will take care of the supply licensee. So this is the structure based on that 2014 amendment bill. So this is what we prepared at that time. Now, what is this LMP? LMP means locational marginal price. I said again, if you want to operate the network optimally, you have to play with the DG units or DG warners. So you have to motivate them. You have to control them in such a way that they are contribute for the optimal operation of a distribution network. They are contribute to optimal operation of a distribution network, right? So what we have to do? So to maintain a fair competition among the private DG owners, that LMP competition is required. LMP nothing but the some financial incentives given to the DG units and the DG owners. So with that financial incentives, with that LMPs, locational marginal price, it helps to maintain the fair competition among the private DG owners. And to encourage the private DG owners for improving the active distribution system operation optimally, and to estimate how much power either supply licensee or provider of last resort need to be purchased from the pool market. Let's assume in a distribution network, there is a load of 20 megawatt. There is no need of purchase the 20 megawatt from the main pool market, from the main grid. There are some DG units, right? So first we have to calculate how much power those DG units will supply for your network. Whatever the remaining power is, that you have to purchase from the pool market. That is the third point. To supply electricity to customers at low price. So it helps to supply the electricity at the low cost. Definitely. To operate the network optimally in terms of the losses and also in terms of the emissions. Also reliability, also voltage stability. So all the things, the main parameter you can play is LMP, locational marginal price. Simple term, financial incentive. You have to give the financial incentives to the DG owners such that that incentive will motivate the DG owners to contribute more in the optimal operation of the network in terms of the losses or emissions, whatever it may be. So here we are trying to discuss about the economic generation, active power losses, based on the active power losses. So why active power losses, especially in the distribution system? Because in general, 3 to 6% of active power losses in the electric power sector. In electric power sector, out of total losses, active power losses contribution is around the 3% to 6%. Total distribution active power losses in the developed countries are not greater than 10%, whereas in developing countries, it's around 20%. So you have to concentrate more on active power losses in the distribution side also. Because there is a more contribution from the distribution side for the active power losses, because it is operating in the low voltage. Okay, that's why we are taking one parameter for optimal operation of a distribution network is the active power losses. Fine. To calculate the LMPs or to calculate the financial incentives, we have to know. So let's assume tomorrow at 6 o'clock, these are the incentives for the DG units. If you want to tell based on the DG units contribution, first of all, you have to know what will be the load on substation tomorrow 6 a.m. First, you have to know what will be the load on the distribution system at 6 a.m. tomorrow. Based on that load, you have to calculate the losses and everything. Then based on that losses, you have to give the incentives to the DG units. So if you want to give the incentives, if you want to calculate the LMP at the DG units or at the DG buses, first you have to know what may be the total load on the system at a particular moment of time. So for that, you have to forecast the load. So here we are using the artificial neural networks for the load forecasting at that time. So this is the small architecture of ANN, artificial neural network. And the performance of the ANN model is observed in terms of the mean absolute percentage error and the root mean square error. Okay. So here we consider the 3-layer ANN model for the load forecasting. So first layer is called as the input layer, where the input parameters are connected. The last layer is called as the output layer, where the output variable is connected. In between, the middle layer is called as the hidden layer. Okay, I don't want to go much about the architecture and everything because we have only 1.5 hour time, and we have only 50 minutes of time now. So just I'm trying to give some brief all the things. So actually, our approach for this load forecasting is we are trying to forecast the load at a time I of a day D. That means at a particular day D, we are trying to forecast the load at a particular time I. That may be like a tomorrow, day 1 at 6 a.m. or day after tomorrow, day 2 at 6 a.m. So at a particular day at a particular time. D represents the day, I represent the time. So we want to forecast, we want to predict. So what approach, what strategy we followed, that is trying to forecast the load at a particular day and particular time based on, you can see here, features, input features are I minus 4, I minus 2, I minus 3. That means if you want to forecast the load at a time I, and you have to consider the last 3 hours load. That means I minus 1 hour before, I minus 2 hours before, I minus 3 hours before. That load you have to consider as an input. In addition to that, not I minus 4 also, last 4 hours. 1 hour before, 2 hours before, 3 hours before, and 4 hours before. And also the load at the same time, but the 1 day before, D minus 1, and 2 days before, D minus 2. That approach we followed here. Okay. So for example, with a small case study, if I want to explain, now the time is around 8 to 10, right? Now I want to forecast the load at 9 o'clock. So if you want to forecast the load at 9 o'clock, what are the inputs as per this discussion? What are the inputs I'm trying to consider? Last 4 hours load. That means what will be the load at 8 o'clock already available, because now time is 8:10. Load at 8 o'clock already available. So load at 8 o'clock, at 7 o'clock, 6 o'clock, and 5 o'clock. Last 4 hours load data, and same time but last 2 days. That means what will be the load at 9 o'clock yesterday, what will be the load at 9 o'clock day before yesterday. So those 6 parameters I am trying to consider the inputs. And based on these 6 parameters, we are trying to forecast the load. So in such a way that we developed the ANN model, neural network model, right? Now, what are the steps followed to solve the problem with AIO? Not only this load forecasting, any problem, how we can, steps we have to follow. First, you try to understand your problem statement very carefully, and you have to decide in what way you want to solve the problem, what approach you want to follow. Based on that approach, you are able to identify what are the inputs and what I am trying to predict, what I am trying to forecast. That you have to get an idea. Once that idea is coming, these are the inputs and this is the output, then you have to start collecting the data. So first you have to prepare the data. You have to collect the real-time data from the substations on which you are trying to work. So that's the first step. Prepare data based on how you want to solve the problem. Prepare the data based on how you want to solve the problem. Now, once the data is ready, next is you have to split the data. So I think our previous professor also explained all the things. Just I'm trying to move it fast. So you have to split the data for the training purpose and the testing purpose, and sometimes validation also. So here we consider the 95% of data for the training and 5% of data for the testing. Next, design architecture based on the approach. Design the architecture means how the ANN will be. How many neurons in the input layer, how many neurons in the output layer, how many neurons in the hidden layer, and how many hidden layers you want to consider. All the things we have to discuss. That's the architecture. Now, data is ready. Your training data is ready. And architecture is ready. Next step is you have to train the network with the training data with the proper algorithm. You have to train your neural network model with the training data and the proper algorithm. Right? If the validation data is available, actually the data is splitted training and testing in generally. Sometimes it is splitted as a training, validation, and testing. Okay. So simply training data is used to train the model. Validation data is used to test the model during the training. Test data is used to test the model after training. These things you have to remember. Okay. So if you want to ask me in a simple way, the data which we demonstrate, which we teach in the classroom, it's like a training data. The data that we will give to the student in the mid examinations, that's like a validation data. And the questions are the data which we will give to the students in the end examinations. It's like a test data in a simple way. Okay. I can explain much more, but okay, I'm trying to touch it up everything like this only. Now, once the training was over, now you have to test your model. You have to test the performance of the model based on the test data. Test the performance of the model based on the test data. In case if the training errors and testing errors are very small and you are happy and your client also very happy, then you can use that model for the load forecasting in the real time. You have to deploy it and forecast the load in the real time. So that are the steps you have to follow, general steps. So here we applied the back propagation algorithm and our samples are like this only. Like I'm trying to forecast load L of t at time t based on the last 4 hours load data, t-1, t-2, t-3, t-4. And same time, but last 2 days, that means d-1, d-2. Like that, you have the multiple samples. Here I'm presenting only 2 samples. You have the multiple samples. With those multiple samples, you have to divide for the training purpose and also for the testing purpose. And you have to train and test the models. Fine. So this is how we are going to use the ANN model for the load forecasting. Fine. So with this approach, you are forecasting the load tomorrow 6 a.m. or tomorrow 7 a.m. or whatever it may be at a particular time, you are forecasting the load. Fine. But our goal is to calculate the financial incentives of the DG units so that your network will be operated at the minimum losses or your network will be operated optimally in terms of the losses. Right? Hope you are clear. If you have any doubt, you can unmute yourself. You can ask in between also, no problem. Okay, so as of now, we are assuming that the forecasted load is available. If the forecasted load is available, then how you are going to calculate the LMPs? How we are going to calculate the financial incentives? Right? That is, so the many concepts come inside. So just I'm trying to give a touch up all the things. So if you want, you have going to in depth, but I'm trying to give as much as possible to make you easy understanding. So coming to the backward and forward sweep algorithm. So backward forward sweep algorithm trying to, so actually why you require backward and forward sweep algorithm? Because backward and forward sweep load flow algorithm is one of the load flow technique that will be used in the distribution system. So we all know the load flow techniques that are used in the transit system like Gauss-Seidel method, Faraday-Coulomb method, Newton-Raphson method. But we can't use, it's not suggestible to use the same load flow techniques in the distribution side also because the characteristics of the network is different. R by X ratio will be different for the transmission system and also distribution system. If you apply the same technique, load flow technique in the distribution system also, there's the possibility that your algorithm may not converge, it may diverge. That's why there is some specific load flow techniques are developed by the researchers specific to the distribution system. So one of the load flow technique is called as the backward and forward sweep load flow algorithm. Okay, so that's why I said many things are come in the presentation. You have to work well on those things if you want to understand. Now, how this backward forward sweep algorithm will work, I'm trying to explain with small calculations. So I think I'm not sure we'll get the sufficient time or not. Okay, fine. So first, let me explain the, okay, we have the 820. Okay, fine. So coming to the, let's assume, I'm trying to explain this backward and forward sweep load flow algorithm with the sample calculations. Small correction here, that is, this generator 5, distributed generator, is not in the 5th bus, it is connected to the 3rd bus. Okay, because it's my small mistake. This generator is connected at the third bus, not at the fifth bus. Now coming to the sample system, the line 1, so this is the line 1 connected between the bus 1 and bus 2, bus 1 and bus 2. At the bus 2, the load is P2 and JQ2. Active power is P2, reactive power is Q2. The values are 0.3 per unit and 0.2 per unit, P and Q values. And this line resistance and the reactance values also available here. Similarly, second line, third line, fourth line, and fifth line. Whereas DG4 is connected at the fourth bus with a capacity of 0.7 and 0.5. That means 0.7 per unit of active power, 0.5 per unit of reactive power is injected into the network at bus number 4. But at the same bus number 4, small thing you have to understand. This DG4.7, DG4 is connected at the bus number 3 here as per this data. Just a minute. I think, yeah, no. Yeah. So this is my network, right? Small corrections here. This is and I want to keep the data also as well. These are my line and bus data information. Sorry. Yeah. No, it's good. Okay, fine. No, it's coming here. Yeah. Small corrections. That is, there is a one generator at so there's one generator at bus number 4. At the bus number 4. So this generator is DG5. Okay, and the generator, there is no generator here. The generator which is connected at the bus number 3, it is called as the DG4. Its capacity is 0.7 and 0.5. P value is 0.7 and Q value is 0.5. Now you can see on the first bus, sorry, on the second bus, the load is 0.3 and 0.2. So here the load is P2 is 0.3 and Q2 is 0.2, right? And at the third bus, the load is 0.4 and 0.3. The third bus is this one. This P3 value is 0.4 and this Q2 value is 0.3, right? But effective load will be changes because this is the load leaving and this is the generation is entering. So an effective load or an effective injection at this point equal to injection at this point equal to P value is 0.7 injection minus load is 0.4. So that's equal to 0.3. That's equal to 0.3. Sorry. Okay. So sorry, is a withdrawal. I'm trying to calculate withdrawal. Withdrawal is 0.4 minus 0.7. That's equal to not sorry. Here DG4 at bus number 3. So bus number 3, the load is 0.5. Load is 0.5. And here the load is 0.2. Here the load is 0.2. What is the net load here? The net load equal to 0.5 minus 0.7. That's equal to minus 0.2. This part. And similarly, here it is a 0.2. This is the 0.1. Sorry, it is a 0.1. It is a 0.1. So you have to calculate your load value minus your generation value. So that effective load you have to calculate at every bus. Okay. Now, after that, what you have to do is, sorry, after calculating the net loads at every point, then, so you can see 0.5 is there, right? 0.5 minus 0.7, that is the minus 0.2. 0.2 minus 0.5, that is the minus 0.3, right? And here it is a 0.1 minus 0.3, that is the minus 0.2. Here 0.3 and minus 0.5, that is the minus 0.2. That means at the fifth bus you have the DG5, whereas at fourth bus you have the DG4. This is your net effective loads. So once the loads are calculated, effective loads are calculated, now first step is, as per your backward and forward sweep algorithm, first step is you have to initialize your flat voltage profile. So that means you have to initialize the voltage at every bus in your distribution network equal to 1 plus J0. 1 plus J0. So how many buses here in your system? We have the 1, 2, 3, 4, 5, 6 buses, right? For every bus, you assume the voltage equal to 1 plus J0 at V1, V2, V3, V4, V5, V6 equal to 1 plus J0. Okay. So now, after initializing all the things, now find the total apparent power injected into the bus. Apparent power injected into the bus. The values are given in load values, right? Load value is 0.3 plus J0.2. It's a load. If I want to calculate injection, then it becomes minus 0.3 minus J0.2, right? So 0.3 and 0.2 are the loads. And I'm asking you, what is the, in terms of the injection, then you can call it as a minus 0.3 minus 0.2. Opposite to that one, right? So that's why the powers are minus 0.3 minus 0.2. S2, why? At S2 means at bus 2. At bus 2, what is the load? 0.3 plus 0.2. That means 0.3 plus J0.2. It's a load. If I'm asking you injection, minus 0.3 minus J0.2. Similarly here, minus 4 minus J0.3. These are the apparent power at the second bus, apparent power at the third bus. Like that, you can calculate the apparent powers at the different buses. Apparent power at the fourth bus equal to 0.2 plus J0.3. Why? You can see at the fourth bus. At fourth bus, so it is the minus 0.2 minus 0.2 minus 0.2 minus J minus 0.2. But if you want to calculate injection, then it will give minus values, right? That's why you're getting the 0.2 and plus 0.2, right? So once you got all these values, you have to calculate the apparent power values. Then you have to calculate the bus currents at every bus. Bus current equal to your apparent power divided by voltage and complex conjugate. So we know that V into I conjugate equal to P plus JQ, S. And I conjugate equal to S by V. And I equal to S by V whole conjugate. So that's what here it is. And you have to calculate the values of the bus currents. Calculate the values of the bus currents. Bus currents, net bus currents are injected. These are the injected currents. Once the injected currents are calculated, now you have to calculate the line currents in the backward sweep. Backward sweep means you are going in the backward direction. In the backward sweep, you have to calculate the line currents. Line currents means bus currents are capital I6, capital I5, capital I4, capital I3, capital I4, and capital I2. All these things are called as the bus currents. Okay. And small I1, small I3, small I2, all are called as the line currents. Bus currents are already calculated here. These are capital I values, all are the bus currents. That's how we can calculate. Bus current equal to, at that bus, what are the apparent power S divided by what are the bus voltage V whole conjugate. Now, if you observe here, what is the line current I5? Small I5 equal to minus bus current. Small I5 equal to minus I6. So I6 already calculated here. I6 equal to minus 0.4 plus J0.1. So line current I5 equal to minus I6. So it is a 0.4 minus J0.1. Similarly, coming to the I4. I4 equal to minus I5. Whereas I5 equal to 0.2 minus J0.2. So small I4 becomes minus 0.2 plus J0.2 because we have to take the negative to all the things. Okay. And coming to the I3. I3 means this one. You can see here I3 this one. So sum of the currents entering into the bus is equal to sum of currents leaving from the bus. Currents entering into the bus equal to small I3 plus capital I4 equal to small I5. Okay. And small I3 equal to small I5 minus I4. Small I5 minus I4. So you can calculate the line current I3. Anyone can tell me what will be the anyone? Small I2 equal to? Small I2 equal to? If you go for the bus number 3, currents entering small I2 plus small I3 equal to I4. Small I4. I want the small I2, line current I2, that's equal to small I4 minus capital I3, small I4 minus capital I3. This is the value. Like that, you can calculate the line currents in the backwards. If I'm coming from the backward, first I calculate the I5, I4, and I3, and I2, and I1. I'm coming in the backward direction and calculated the line currents. Calculate the line currents, right? So actually, while coming to this session, I thought of explain all the things with numericals, but because of that constraint in the time, so I'm explaining the slides only. But I hope you are able to understand. First thing is, you have to calculate the loads at every bus. If you have any DGs at a particular bus, then you have to calculate the load at that bus. That's it. Actual load minus your generations. That will give the actual load. Sorry, resultant load at that bus. After that, you have to assume the flat voltage profile. After that, you have to calculate the bus currents based on the powers and based on the flat voltages. After that, in the backward sweep, you have to calculate the line currents. Next, backward sweep is completed. Now it is a forward sweep step. In the backward sweep, we are going to calculate the line currents, whereas in the forward sweep, we are calculating the voltage at each bus. Substation bus always 1 plus J0. We no need to update. You have to update the bus 2, bus 4, bus 3, bus 6, and bus 5 voltages. We have to update it. How you will update? The voltage at bus 2 equal to bus 1 voltage, substation voltage 1 plus J0 minus drop in this line. Minus drop in this line. Similarly, if you want to calculate the voltage at V4, if you want to calculate the voltage at the bus 4, then bus 2 voltage minus a drop in the third line. Drop in the third line is nothing but the current in the line I3 into impedance of the line Z3. You have to subtract, drop. Right? Similarly, if you want to calculate the V3, then your voltage V2 minus I2 into Z2, where I2 is the current in the second line, Z2 is the impedance of the line. Similarly, anyone can tell me how I can calculate how I can update the V6? Anyone, please? How I can update the V6 voltage at the bus number 6? How I can update the voltage at the bus number 6? Anyone? How we can update the voltage at the bus number 6? Any idea? How we can update the voltage at the bus number 6? Let's assume I know the voltage at the bus number 4. We already calculated. First, we know the 1 plus J0 is the common. And this voltage minus a drop here, it will give the voltage at the second bus. And once we got the second bus voltage, now calculate the bus 4 voltage. Bus 4 voltage equal to this voltage already calculated minus a drop here. Similarly, bus 3 voltage, the voltage at 2 is calculated minus this drop will give the breath. And now I'm asking how we can calculate the bus voltage 5, voltage at the bus number 5. Anyone? Okay, fine. So this is how we can update the voltages. My second bus voltage equal to my from bus voltage, initial voltage V1, substation voltage minus the drop in the first line. That will give the voltage. Previously, I'm assuming that V2, V3, V4, V5, V6, V1 are the flat voltages. Now, my voltage V2 equal to updated as 0.97 minus J0.2. It is updated voltage. Similarly, V3 equal to V3 is connected to V2. So V2 minus drop in the second line. This value we are getting. Similarly, V4 equal to V4 is connected to the second bus. So V2 minus drop in the third line. This is the voltage. Like that, you are able to update the voltage at V2, V3, V4, V5, and V6. Once the voltages are updated, now calculate the new powers. Already we calculated in the initial step. These are the old voltages. Now updated voltage we have to updated powers we have to calculate, apparent powers. So you have to use the updated voltage V2 and current I2 conjugate. Similarly, V3, I3 conjugate, V4, I4 conjugate, V5. Where V2, V3, V4, V5, V6 are the new voltages. Updated voltages. With these updated voltages, you have to calculate the updated apparent power at every bus in the distribution system. So these are the values. Now calculate the difference between your initial voltages, initial apparent power and your updated apparent power. calculate the difference and calculate the magnitude. If this difference is maximum difference is less than some value 0.001 or 0.0001, then you can stop the algorithm. Otherwise, again, go for the second iteration. Again, calculate the line currents in the backward sweep, update the voltage in the forward sweep, calculate the apparent power at every bus, calculate the difference between the current apparent power and previous iteration apparent power. And if this apparent power difference is less than 0.0001, then you can stop the algorithm. So this is the process that we will use for the backward and forward sweep algorithm. Actually, my intention of when coming to the session, my intention is I want to explain step-by-step process of the backward sweep on a whiteboard, and I want to program it in the MATLAB. But it's okay. You have some idea, right? So in FDPs, you don't expect programming, calculations, everything is in this session of 1.5 hours. But you have some idea, some glance how to apply the load flow technique for the distribution system. If you explore more, then you are able to implement in the MATLAB or Python, whatever it may be. So this is about the load flow technique. So this load flow technique we are applying in our distribution network to calculate the losses. Okay, I'm moving further fast. Now that's why I say there are multiple things in that complete session. I'm trying to discuss about the or problem statement. I'm trying to discuss about the AI neural networks. I'm trying to discuss about the load flows. I'm trying to discuss about the optimization also. This is the optimization. Okay. So the optimization concept also required for this to solve this problem statement, especially linear optimization. So linear optimization means where objective function is linear. Now, so like your mathematical modeling of any objective function, mathematical modeling of any linear programming problem is like this. You have some objective function. You have to minimize that objective function. And you have some inequality constraint, you have some equality constraint, you have some boundaries. Like that, you have the mathematical model. Okay. Where your f of x is a linear in terms of your decision variable x. That's what's called the linear optimization problem. So we can solve this linear optimization problem and using MATLAB or using Python, using the linprog method. Linprog is one of the method that is in the MATLAB as well as in the Python to solve the linear programming problem. Okay. So this is a small case study how this linear optimization problems are, but I want to skip this part. So this is the actually problem given by the client. As an engineer, I have to convert this problem into the mathematics. So I'm converting that problem in the mathematics. Okay, and I have to solve this one in terms of the MATLAB. So let's assume I want to so how we solve this one. So I will explain if possible. So this is my problem, right? Now go to whiteboard. Now this is problem. Now if you want to solve this linear optimization problem using your MATLAB, then you have to form a objective function matrix. Objective function matrix equal to your coefficients. What are the coefficients in your objective function? 6 and 5. So because it's the maximization problem, but your MATLAB linprog method supports only minimization. So that this maximization problem, I want to convert it to minimization problem, simply multiply with minus sign. So that means the coefficients in the object function are -6 colon -5. Similarly, now convert this one into the mathematics like a matrix. So I want to convert this one as a matrix like x coefficient is 1, y coefficient is 1, x coefficient is 3, y coefficient is 2, and multiply with my decision variables x and y. That should be less than or equal to 5 and 12. So this matrix is called as the A matrix. This matrix is called as the B matrix. And coming to the boundaries. So lower boundary, x and y should be greater than 0. So lower boundary is 0 and 0. And upper boundary, you no need to mention. It is like infinity. No need to mention. So you have to get the A value. You have to give the B value. You have to give the F value. You have to give the lower boundary values. to the lean-prog method. So lean-prog method expects few things like your function f, a value, b value. These are for the inequality constraints, and you expect the a equivalent and b equivalent. This is for the equality constraint, and it expect the lower boundary and upper boundary, and some options it will expect. Options means which algorithm you want to use. Okay, so suppose if you want to uh, okay, fine. So the time is not sufficient for me. So simply MATLAB, you can write a code like this: x, that is your x and y values it will have, and f, that will give your object function value at optimal object function value, that's equal to. You can write linprog. You pass your f matrix f, you pass your a matrix a, you pass your b matrix b, and there is no equality constraint, right? Simply click, simply yeah. You may write f equal to minus 6 colon minus 5, and a equal to 1 1, I think 1 1, and what are the another values? 3 2. So 3 and 2, that's the a value, and the b value equal to, what are the b value? 5 and 12. So 5 colon 12, and what's the lower boundary? Lower boundary, I said that lower boundary equal to zeros, right? See, you can see the lower boundaries x comma y should be positive, greater than or equal to 0. That's why lower boundaries are 0. Okay, and you can write one more thing: options. You have to mention options equal to sorry. You have the options, and you have to call linprog. You have to call linprog, and you have to tell the algorithm, and I'm giving the dual simplex method. Okay, so now I want to find the solution, right? That is x equal to, or you can write x is the optimal values of x and y, and f is nothing but the object function, optimal object function value, that's equal to, you can write linprog and open. You have to pass your f, you pass your a, you pass your b. There is no equality constraint, a equal to empty, b equal to also empty, and lower boundary is lb, and there is no upper boundary values, and you have to pass the options. Sorry, you have to pass the options. Sorry. Options, right? That's it. You can simply save this code somewhere, and you can run this one. Yeah. So finally, to give the solution, it's saying that optimal value of x equal to 2 and optimal value of y equal to 3. That's how we can solve the linear programming problem. Sorry for extending this topic for much time. So this is how we can solve the linear programming problem using the what's called MATLAB. You can do it in the this one also, the Python also you can do it. So next one is nucleus theory. This is one of the game theory concept. So how we apply this game theory concept here is, let's assume in my distribution system I have the 3 DG units. Without the DG units, it is called as the base case losses. Without DG units, it is called as the base case losses. Without DG units, it is called as the base case losses. Now, if you want to use the game theory, the approach you have to follow is, you have the 3 generators, right? Now connect only one DG, run the load flow, and these are the losses. And whatever the loss reduction, 220 minus 207, 12.7 is my loss reduction. Okay, sorry. And now connect the only second DG and run the load flow. Now the losses are 200. 220 minus 200, approximately 20. Similarly, connect the third DG unit and the losses are 205 and the difference is 14.6. Now I have three DGs, right? Now connect 1 and 2, run the load flow, calculate the losses, calculate the difference. Next connect 1 and 3, calculate the losses, calculate the difference. And 2 and 3, calculate the losses, calculate the difference. And connect all three units, calculate the losses and calculate the difference. So this column is called the loss reduction after connecting the DGs. These are the losses after connecting the DGs. These are the base class losses, base case losses without connecting the DGs. That's we have to do as part of the game theory for the loss allocation. So here I am using the nucleus theory is one of the game theory concept for the for allocation of the losses among the DG units. Allocation of the losses. Yeah, DG1 contribution in the loss reduction is this amount of megawatt. DG2 contribution in the loss reduction is this amount of megawatt. DG3 loss contribution is this amount of megawatt. If you want to allocate contribution of every DG unit in the loss reduction, then we have to go for the game theory concept. And here we are using the nucleus theory concept. All right. So in the nucleus theory concept, first thing is you have to do like this. You have to calculate you have to run the load flow for the multiple combinations of all three DG units and calculate the loss reduction for every case. Okay. Now, 1 minute. The load flow is completed, optimization completed. Okay, fine, no problem. So, is my screen is visible, right? Yeah, I think it's visible for you.
Visible, sir.
Right, fine. Thank you, sir. So after calculating this loss reduction, now you have to go for this optimization problem as part of your nucleus theory. So what this optimization problem is, just I'm trying to explain slightly. So game theory, nucleus theory, mathematical modeling is minimize epsilon is a small value. You are trying to minimize this one. So V of K, that is called a correlation, minus sigma of Yi, this is the contribution of the every DG in the loss reduction, that should be less than or equal to epsilon. And capital V, this small v, capital V is called the grand correlation. Grand correlation means which contains all DG units, 1, 2, 3, minus sigma Yi less than or equal to epsilon. Okay. So what is this one? So this is the linear optimization problem. So I will explain, don't worry. So previously we calculated one thing, right? That is, yeah. So when only one DG connected, what are the losses? 12.7. So that means, so V of 1 equal to 12.7. That means you have to write this equation as V of 1, that is the 12.7, and V of 1 means only DG1 is connected. That means minus Y1 less than or equal to sigma, epsilon. Similarly, next is the V of 2, only second DG is operated. So what is the V of 2 value? 19.9. So 19.9 minus the second DG, right? So it will be the Y2. Y1 is the contribution of the DG1, Y2 is the contribution of the DG2, less than or equal to epsilon. Okay. And what about next to third one? 14.6. So 14.6 minus is the third DG, third distributed generation unit. So minus Y3 less than or equal to epsilon. Coming to this point, it's the combination of 1 and 2. What is the last reduction? 70. 70 minus is the combination of 1 and 2. So you can write it as a Y1 minus Y2 less than or equal to epsilon. Okay. This part I'm explaining, this line. Okay. Now, what about next one? 1,3. 1,3 how much? 40.8. So 40.8 minus Y1 minus Y3 less than or equal to epsilon. And what about next one? 2,3. 2,3 value 56.7. So 56.7 minus Y2 minus Y3 less than or equal to epsilon. Okay. So these all are the related to this equation. And last one is the grand correlation. That means combination of all three. What are the value? 112.1. That means 112.1, which has all the three generators. That's why minus Y1, minus Y2, minus Y3. Or you can call it as a, so sorry, it's not, it's equal to. So it's equal to 112.1 equal to Y1 plus Y2 plus Y3. So this is, you can call it as a equation number 2. You can call it as a equation number 1. And your object function is a minimization of epsilon. You can write it as a minimize 0 into Y1 plus 0 into Y2 plus 0 into Y3 plus 1 into epsilon. This is what? So if you can see, it is minimizing some objective function subjected to some inequality constraint and subjected to one equality constraint. That's why it's called as a linear optimization problem. Now apply your linear programming, that what I explained in the MATLAB. You can apply the same linear programming problem here and solve it. Then you can get the contribution of what the Y1 value you will get, and what the Y2 value you will get, and what the Y3 value you will get. So these values, what we are getting is the contribution of the distributed generation 1, contribution of the distributed generation 2, contribution of the distributed generation 3 in the total loss reduction when 3 operated collectively. When 3 units are operated collectively, the total loss reduction, let's assume 10 megawatt. Then what will the contribution of the DG1, that is called as the Y1? It may be 2 megawatt. And what is the contribution of the second generator? It may be 3 megawatt. What is the contribution of the third generator? It may be 5 megawatt. So like that, you can use the game theory to find the contribution of the every DG unit in the loss reduction, because I'm considering the loss reduction as a parameter to observe the optimal operation of the distribution network. So this is the game theory or nucleus theory, which is used to find the allocation of the each player, each DG unit in the loss reduction. The main purpose of the nucleus theory. Now, so finally, I am getting after game theory application, finally I'm getting that DG1 contribution in the loss is the 40.40 kilowatt, and DG2 contribution is a 33.20 kilowatt, and DG3 contribution is a 38.50 kilowatt. That's the contribution of every unit in the total loss reduction. If you add all the three things, you will get the 112 value, approximately 112 megawatt, 112 kilowatt you will get. Because the contribution of the DG1, contribution of the DG2, contribution of DG3, if you add 3 contributions, that should be equal to total loss reduction, 1 to 1. Okay, otherwise your solution will be wrong. Okay, this is about the allocation of the losses using nucleus theory, and the performance of the nucleus theory is observed based on the 3 aspects. One is called the individual rationality, correlation rationality, and collective rationality. So individual rationality is nothing but when only DG1 is operating, whatever the loss reduction, that should be less than DG1 contribution when 3 units are operated. That is called as individual rationality. Once again, I will tell, individual rationality means whenever any one generator is operating alone, then the total loss reduction should be less than the contribution of the DG2 when all 3 generators are operating together. If that was happening, that is called as individual rationality. That should be true. If your game theory, if nucleus theory performing better means these things should be satisfied. Similarly, coalition rationality. Coalition rationality means, let us assume here correlation of 1, 2. That means DG1 and DG2 are operating. When DG1, DG2 are operating collectively, 70 kilowatt is my loss reduction. But when 1, 2, and 3 are operated, when I add the contribution of the 1 and 2, the value is 73.6. That should be more when compared to only 1 and 2 are operated. If the 3 units are operated, whatever the contribution of 1 plus what is the contribution of 2, that should be more when only 1 and 2 are operated in the distribution system. That is called the correlation rationality. And it is a collective rationality. Collective rationality means whenever 3 units are operating, the contribution of the every unit, sum of the contribution of the every unit must be equal to total loss reduction. That is called as the collective rationality. Okay. So these 3 things must be satisfied. Then only you can say that your solution is perfect. Now, actually, in this algorithm, next coming algorithm, I will explain. I'm using one parameter called bus incidence beyond line matrix. So, bus incidence beyond line matrix means you can see the line one. So, line one buses incident in the beyond the line. So, beyond the line. So, beyond the line, what are the buses are there? Second bus, fourth bus, third bus, fifth bus, and sixth bus. That's why all are ones. And if coming to the line number 3, IL3. If you're coming to the line number 3, so what are the buses beyond this line 3? Bus number 4 and bus number 6. So you can bus number 4 is 1 and bus number 6 is 1. Like that, we are preparing the bus incidence beyond line matrix. And why you are trying to build this one? Because you have to read this iterative algorithm. In that iterative algorithm, we will use this part. And coming to the iterative algorithm for this financial incentives calculation, first, you have to read at what day, at what time you want to calculate the financial incentives to minimize the losses. For that time, for that day, you forecast the load based on the ANN. And for that time, you have to estimate the market price also. Next step is you have to calculate the generation of each DG unit based on your market price using this formula, where B and A are called as the cost coefficients of your DG units, like our economic load dispatch we studied in the power system deregulation, in power system operation control. So like that, here also we are going to calculate the generation of each DG unit based on the market price. And based on the power factor, we are calculating the reactive hour of the generator also. After that, run the load flow in the base case to calculate the base case losses. From the load flow at different combinations. If your distribution network has a 3 bus, actually the results what I'm going to show is a Taiwan Power Company distribution network containing around 84 buses, and it contains 15 DG units. So you have to run the load flow algorithm with the generator 1, run the algorithm with only generator 2, run the algorithm with only generator 3, run the algorithm with only generator 15. Later 1, 2, run the algorithm, 1, 3, run the algorithm. Okay, so for all the combinations you have to try. Actually, while working on this project, for me it took more than 24 hours. Just I run the code and a system, and I will go to my home and I come to the next day. So that will take the more time. So if anyone going for the research further, try to come with some solution so that the computation power and the iterative time will be reduced. You can think in the direction. Well, so, okay. Now you have to calculate because of the loss reduction, whenever the DGs are connected, definitely your losses will be reduced. Because of the loss reduction, there will be some financial incentive, some financial benefit. When there is a loss reductions are there, distribution company got some financial benefit. Now that financial benefit, they don't want to keep with them. This is the extra benefit they are getting. They will got the financial benefit from the customers. They will purchase the power at some price. They will sell that price at the higher price to get the profit. But what this benefit is, the additional benefit because of the DG units, because of the loss reduction. Whatever the benefit is there, that should be distributed back to DG units so that they will be motivated. So how it will be distributed? The DG which contributed more in the loss reduction, we have to give the more price to them. And the DG which is less contribution in the loss reduction, they will get the less price. So for that one, these are some steps. How we calculate the DG incentive, that is based on the contribution of the ith DG in the total loss reduction and multiplied with your market price. Multiplied with market price. So based on the loss contribution, it will get the incentive. Okay. That means if the generator contribute more in the loss reduction, they will get the more price, less in the contribution, they will get the less price. Based on their performance, we are going to give the incentives. And again, in the incentives also, for the active powers and the reactive powers also, we are further distributing based on this BIBL matrix. You can see here, BIBL matrix. And BIBL matrix, I explained earlier, bus instance beyond line matrix. So based on this BIBL matrix, calculate this change in losses with respect to the reactive power and active power, and calculate the share, active power share and reactive power share in the loss reduction. And based on this share, you can calculate the incentives for the active power and the reactive power. And further, based on the incentives, again, you have to calculate the new generation and new price you have to calculate. So this is how your iterative algorithm will work. Okay. And coming to the results, so as I said earlier, so I am taking a TPC, Taiwan Power Company distributed system, which has the 84 buses. In 84 buses, I have the total 15 DG units. So these are the unit number, 15 DG units. These are the type of the DGs. There are the different types of DG units are there. Type 1, type 2 types like diesel engine, internal combustion engine, gas combustion engine, different type of DG units are there. And these are the locations where they are connected. One bus is connected at the 4, one bus at the 84, one bus at the 60, one bus at the 76. At different locations, all the 15 DG units are connected. And so these are the incentives. Then the market price is 19.23. This is the less than the B value, so that see how you can calculate the power P. P is calculated market price minus B. But when the market price is 19.23, this 19.23 is less than the B values of all the generators. When this value is less than the B value, then this will become negative. Negative generation means no generation. If there is no generation, there is no incentive. Because there is no generation, there is no loss reduction, there is no loss share, there is no further incentives. That's why in that case, all have the same price. And whereas when the lambda equal to 21.59, market price is 21.59, but different generators got the different prices based on their contribution in the loss reduction. Similarly, at 25.07, different have the different, see, different generators have the different prices. If you observe one thing, DG number 11 has 22.62 price when the market value is 21.59. And similarly, it is a 26.21 when the market price is 25. And among all the DG units, your DG 11 price is very high. Why? Because the 11th distributed generator contributes more in the loss reduction when compared to the remaining 14 generators. That's why it's got the more incentives when compared to the remaining generators. Similarly, so as the iterations of progresses, your losses also reduced as we are giving the incentives to the DG, which contributes the more in the loss reduction, right? So this is a slight results of some results I have posted. Many results are there here. Just only for this purpose, I'm posting something. Okay. So this is all about my session as per the schedule. So I took 4 minutes extra.
Problem, sir.
Yeah. So this is all from my side. So if you have any questions, you can ask, or if not possible, right moment. But if you are working anything related to the LNPs or load forecasting in the distribution side, so you can approach me also. We can collectively work together if possible. So if you have any questions, please.
Okay, sir.
Yeah.
Thank you, sir.
Thank you very much, sir.
Thank you for your valuable session about AI and ML in distributed energy resources. And in that session, how to improve the operation of is a DC and how to reduce the losses in the DC, and what about the load forecasting at different times, and also algorithms and MATLAB session for calculating bus voltage and losses. Thank you, sir. Thank you for your valuable information.
Yeah, thank you, Anil sir, for giving this opportunity. Thank you, sir. So, can I leave, sir? Sir, any questions from the participants, or I leave?
Any questions? No problem, sir.
Okay. Thank you very much, sir. Anil, sir.
Okay, sir.
Bye, sir.
So please leave the session right now.